Good morning, students. So far we have been learning about matrices, the properties of matrices, especially the adjoint of a matrix, cofactor of the matrix, rank of a matrix, and in the last class we discussed about the characteristic equation, eigenvalue problem, eigenvectors, and all those things we discussed. And of course, Cayley Hamilton theorem is a continuation of the characteristic equation. And in fact, it is defined as a square matrix satisfies its own characteristic equation. So that's the definition for Cayley Hamilton theorem. And from Cayley Hamilton theorem, of course, we will get, suppose we are going to take a matrix, just take a matrix. We will get a polynomial equation. So a matrix that will transform into a polynomial equation, which satisfies its own matrix. What we call this as Cayley Hamilton theorem. And out of Cayley Hamilton theorem, one can easily obtain the inverse of a matrix. Not only inverse of a matrix, but also the squares of the matrix or any power. Any power of a matrix can be obtained from using Cayley Hamilton theorem. For example, you have a matrix A, a square of the matrix A squared, A to the power 3, A to the power 5, A to the power 10, A to the power 20. So all those powers can be obtained using Cayley Hamilton theorem. So this is very, very useful theorem, and which we are going to solve using some problems. And the next title that we are going to discuss today is on diagonalization of the matrix. Diagonalization of the matrix is very, very important, not only in mathematical physics but also in quantum mechanics. When you are going to diagonalize a matrix, you are getting only diagonal elements. Those diagonal elements are eigenvalues of the matrix. So you have a matrix and we are going to write in terms of diagonal elements. These diagonal elements are eigenvalues of the matrix. So that's the idea. Now this diagonalized matrix is used in quantum mechanics. And of course we know the quantum mechanics starts with the Schrodinger wave equation. Schrodinger time independent wave equation is nothing but eigenvalue equation. So one can get the energy eigenvalues using the eigenvalue equation. Not only Schrodinger wave equation but also in perturbation theory. Perturbation theory, which deals with some perturbation, some disturbance with the Hamiltonian, and that will be changed into certain level. So perturbation theory with a degenerate case is nothing but eigenvalue problem. So in two major problems it is used, the diagonalization is used. One is Schrodinger time independent wave equation, another one is in perturbation theory. But also in latest computers we have numerical methods where we can learn the variation method. All those things we have to diagonalize the matrix. So diagonalized matrix is very important, and these two techniques that we are going to study today. So first one is Cayley Hamilton theorem. So if just take 2 by 2 matrix, A equals 2, 5, 4, 1. The characteristic equation is given by A minus lambda I equal to 0. Okay. So A minus lambda I, so that is A minus lambda I, which is equal to A minus lambda. Okay. So A minus lambda is given by this matrix 2 minus lambda, 5, 4, 1 minus lambda, which is equal to 0. So we can multiply, cross multiply, you will get this equation. Okay, very simple idea. So we will get the characteristic equation. Okay, just to simplify this one, you will get the characteristic equation. So lambda squared is here, minus 2 lambda, minus lambda will give you minus 3 lambda, 20, minus 20 plus 2, that will give you minus 18. So this is your characteristic equation. As I said just now, Cayley Hamilton theorem says that a square matrix satisfies its own characteristic equation. So this is your characteristic equation. You are going to replace lambda by A. A is a matrix. A is the original matrix. Okay. You are going to change, you are going to replace lambda as A. So this equation becomes A squared minus 3A minus 18I equals 0. A is given as in the problem. So square it. So first we will calculate A squared, square it. Squaring is nothing but matrix multiplication of the same matrix. So you have this matrix, you are going to have a matrix multiplication, you will get A squared. And a squared minus 3a minus 18i, which is nothing but your characteristic equation. So we can write this as a squared minus 3, your a is here, minus 18i. You calculate all those things, simplify this one, you will get 0, 0, 0. So it satisfies its own characteristic equation. Very simple idea. Is it okay? 2 by 2 matrix. Now we will go for 3 by 3 matrix, the same technique. So A is given as 3 by 3 matrix. You have 1, 2, 3, 2 minus 1, 4, 3, 1, minus 1. And of course, use the characteristic equation A minus lambda I equals 0. So A minus lambda I gives you this expression, this matrix minus lambda this matrix. We know already. So simplifying, you will get this matrix. Okay. Now we are going to take this formula which we learned in the last video lecture. Just take this formula, lambda cube minus s1 lambda square plus s2 lambda minus s3 equals 0. What is s1 here? S1 is sum of the diagonal elements, trace of a matrix. So one is over. Then second one, what is s2? Sum of the cofactor of diagonal elements. What is s3? Det value. So determinant value. So now you have to go for the sum of the diagonal elements. That is will be your s1. So just add all those things, that will give you 1 minus 1 minus 1 will give you minus 1. Okay, 1 is over. S2 is, you will have to find out the minus of the diagonal elements. Minus of the diagonal elements. Okay, these are all diagonal elements. You will have to go only with the minus of the diagonal elements. So first diagonal element, the minor will be this one. Second one, we have already one minus is there. So you will have plus. So you have 1, 3, 3 minus 1. And third one is the diagonal element is here. So you have to only go with the cofactor, which is nothing but 1, 2, 2 minus 1. So you add all those things, that will give you minus 18. So your S2 becomes minus 18. Now S3 is det of A, determinant of A. You will get determinant of A, you will get as 40. So we have calculated S1, S2, S3. You substitute in the characteristic equation, you will get this equation. So now we will have to use Cayley Hamilton theorem, which is nothing but A cube plus, replace lambda by A. So A cube plus A squared minus 18A minus 40 equals 0. So first we will calculate A squared first. We will go with A squared. So A squared is A multiplied by matrix multiplication. Your A multiplied by A will give you this answer. So A cube is A squared multiplied by A. A is given as this. Okay, so A squared multiplied by A will give you this answer. So we have calculated now A cube. Is it okay? Now the equation is polynomial is A cube plus A squared minus 18A minus 40I. So this is your A cube, A squared minus 18A minus 40I. So simplifying, after simplifying you will get 0, 0, 0, 0. So Cayley Hamilton theorem is proved. That's all. Simple idea. So we have seen 1, 2 by 2 matrix. Then after that we have seen 3 by 3 matrix too. So now, as I said earlier in the introduction, we can get any powers of matrix. Can you remember? As I said in the introduction, the usage of Cayley Hamilton theorem is, one is inverse of a matrix, which you are going to find out now. The second one is any power of a matrix can be obtained. Now we are going to find out m to the power 6 now. So far we have learned only a cube, m cube. So m to the power 6 now. M is given as this. In the earlier notation we wrote as A equals a matrix. So this is 2 by 2 matrix. M is given as this. We are going to find out m to the power 6 using Cayley Hamilton theorem. So the characteristic equation is nothing but lambda squared minus 5 lambda plus 6 equal to 0. So you have to use that formula. Okay. So lambda squared minus 5 lambda plus 6 equals 0, and this can be replaced with m. Instead of A we have written m, doesn't matter, everything is the same. So different books they follow m, some other books they follow A. So you have m squared minus 5m plus 6i equals 0. So m squared equals 5m minus 6i, correct? Squaring will give you m to the power 4 as this. A minus b whole squared formula. So you have a squared minus 2ab plus b squared. You pull 25 out here. 25 here. M squared can be written as 5m minus 6i. So you have 25. M squared can be written as 5m minus 6i. This as it is, minus 60m plus 36i. Now you can simplify. See, this can be simplified. 25 multiplied by 5 is 125m. 125m minus 60m will give you 65m. 25 minus this one 60, 6, 150 minus 150i minus 150i plus 36 will give you 114i. Simple. So we have simplified now. This is your m to the power 4. M to the power 6 is nothing but m to the power 4 multiplied by m squared. M to the power just now we have obtained. M squared already we know m squared is this one. You multiply these two will give you m to the power 6. That's the idea. So you have m to the power 4 now. This will be your m square. You multiply this by this, multiply this by this, multiply this by this, and multiply this by this. You will get exactly like this. And what is m square? 5m minus 6i. So 325 instead of m squared you write 5m minus 6i. Again you simplify. You will get 665m minus 1266i. Okay. So 6665. What is m? M is given as this matrix. Minus 1266. What is I? I we know 1001. You add these two, you will get this. So this is m to the power 6. See, any power we can obtain. M to the power 6 or m to the power 10, m to the power 20 or 15, whatever may be the power we can obtain. So that's the usage of Cayley Hamilton theorem. Okay, simple one. So I have done here. I have simplified. Find now the another usage, A inverse. Okay, so using Cayley Hamilton theorem. So we'll have to use Cayley Hamilton theorem to get A inverse now. Now matrix is given as 3 by 3 matrix. Use this equation, characteristic equation. Lambda cube minus S1 lambda square plus S2 lambda minus S3 equals 0. Here S1 is the trace of a matrix. S2 is sum of the minor of the main diagonal elements, and S3 is nothing but your det A. So you will get out of this matrix, you will get S1 as 2. Sum of the diagonal elements. 1 will get cancelled, you will have 2. Second one, S2 will be sum of the minus of main diagonal elements. The first minor diagonal element will be this one. 2 multiplied by minus 1, 1 multiplied by minus 1 with plus. So minus 2 plus 1. Then plus second minor of second diagonal element. Okay, this one will be the minor of third diagonal element. You add all those things, you will get minus 5. And S4 is det A. Det A easily you can find out. Det A you will get as answer as minus 6. Now the characteristic equation is given by this. You have to replace lambda by A. So A cube minus 2A squared minus 5A plus 6A equals 0. Any doubt? Now our aim is to find out A inverse. The technique is this one. So the characteristic equation is given as this. Okay. Now you are going to multiply on both sides by A inverse. So A inverse multiplied by A cube will be A squared. Correct? A squared. A inverse multiplied by A squared will be your A. A inverse multiplied by A will be your identity matrix. The last one, 6 multiplied by A inverse will be A inverse itself. So this will become A squared minus 2A minus 5I plus 6A inverse. See, look at this equation. A inverse exists. You just take all those things to this side, or 6A inverse to that side. So you will get 6A inverse equals minus A squared. You bring all those things except the A inverse term, plus 2A1 plus 5A plus 5I. So A inverse equals 1 by 6, the remaining terms. It's very easy. So you have A squared. First you find out A squared. A squared is A multiplied by A. So that is simplified as this one. Next one is 2A. We can do it. 5A also we can do it. Now put together. Minus A squared plus 2A plus 5A will be this one, and this one will give you this. What is A inverse? 1 by 6 of this one. So 1 by 6 of this one. So this is the answer. Simplest one. Okay, using Cayley Hamilton theorem, one can find out the inverse of any matrix. That's the idea. So now we are going to verify Hamilton theorem, A to the power 4 and A inverse. We are going to do simultaneously both. So earlier we did separately the powers of the matrix using some other matrix, then A inverse we did it for some other matrix. Now we are going to do the same thing, the usage of Cayley Hamilton theorem. One is A inverse, another one is A to the power 4 with the same matrix. Now we know that the characteristic equation is given by this: lambda cube minus s1 lambda square plus s2 lambda minus s3 equals 0, where s1 is given as this. Okay, where s1 is nothing but adding all the diagonal elements will give you 6, where s2 will be sum of the minus of the main diagonal elements, that is given as 8, and where s3 is det A, the answer is 3. So you substitute all the terms here, you will get the characteristic equation exactly like this, and you have to replace lambda by A as usual. So we have replaced by lambda by A. Now you find out, now as usual we will have to find out, first we will calculate this. So A squared equals A multiplied by A, that will give you your A squared. So A cube equals, here A cube is there, so A cube multiplied by A, so you have A squared multiplied by A will give you A cube. Okay, then A cube minus 6A squared plus 8A minus 3A, so this is your A cube, this is 6A squared, this is your 8A minus 3A will give you 0, 0. So characteristic equation is satisfied. First we will have to find out whether it satisfies or not. So it has to satisfy, a square matrix should satisfy its own characteristic equation. That is the idea behind Cayley Hamilton theorem. So now we are going to find out A to the power 4 now. Now this is the equation that we have obtained, correct? This is the equation. Now I am going to take as A cube as this side, remaining term I am going to keep it as like this. Multiply on both sides by A, that will give me A to the power 4. This becomes 6A cube minus 8A squared plus 3A, correct? 3A. This 6, instead of A cube I can write the same term. We have remaining term will be minus 8A squared plus 3A. So you just multiply these things. 6 multiply these things, you add these things, you will get exactly 36A squared minus 48A plus 18I minus 8A squared plus 3A. You simplify, you will get this, which is nothing but your A to the power 4. So A to the power 4 equals 28A squared. Already you have calculated A squared earlier. You substitute here. Minus 45A plus 18I. You simplify, you will get this answer. So which is nothing but your A to the power 4. Any power you can get it. So we have finished 50%. So remaining one is your A inverse. You have to find out A inverse. So this is the characteristic equation. As I said earlier, you have to multiply by A inverse on both sides. So you will get A squared minus 6A because A inverse A squared will be 1A will get cancelled. So you have minus 6A. The next one will be plus 8I minus 3A inverse, which is equal to 0. So as I said, you just bring this term to right hand side, you will get 3A1 which is equal to A squared minus 6A plus 8I. So 3A1 equals your A squared is here minus 6, A is here, your I is here. You simplify, you will get this matrix 3 0 minus 3 1 2 0 minus 1 1 3. Divide by 3, 1 divide by 3, that will give you 3A1. Okay, so divide by 3, that will give you A inverse. So we have found out A for a particular matrix, we have found out A to the power 4 as well A to the power minus 1. We have found out. Any doubt? So next one is next topic is diagonalization. So as I said, diagonalization is very important property because we will get the eigenvalues. These eigenvalues can be put it in a matrix exactly in a diagonal elements. Of diagonal elements will be 0. You are going to get eigenvalues. We learnt in the last video lecture how to get the eigenvalues we have learnt. So for a matrix, you just get the values of eigenvalues. Get the eigenvalues. You just put it in the matrix. You will have only diagonal elements alone. That's why it is called as a diagonalization. Okay, that's the idea behind. So what is the usage of this diagonalization? As I said earlier, that especially this is used in quantum mechanics and Schrödinger time independent wave equation as well as perturbation theory with the degenerate case. So both the things it is used not only in quantum mechanics but also it is used in numerical computation, especially using variational method, which we will learn later. So what are the methods? How to find out the diagonalization? So if you learn by heart this slide, it's more than enough to get the ideas of diagonalization. Find first eigenvalues. So you have to get, for a matrix, you have to get eigenvalues first. Second one, eigenvectors. First you have to use A minus lambda I equal to 0 to get eigenvalues. A minus lambda I multiplied by x to get eigenvectors. Is it okay? To get eigenvalues, you have to use A minus lambda I equals 0. To get eigenvectors, A minus lambda I x equals 0. You will get x1, x2 for 2 by 2 matrix. For 3 by 3, x1, x2, x3 you will get it. Everything in terms of rows, you will convert in terms of column. You have to convert this one into column vector. That eigenvectors, combination of column vectors, what we call this as P matrix. I repeat, simple idea. First thing is you have to get eigenvalues. What is the formula? A minus lambda I equals 0. Second formula is A minus lambda I multiplied by x equals 0 to get eigenvectors. For 2 by 2 matrix you will get x1, x2. 3 by 3 matrix you will get x1, x2, x3. You make all those things in a column vector. You combine. Just you combine. When you are going to combine the matrix, you will get P matrix. Okay, you will get P matrix. How to find out P inverse? P inverse equals 1 by A adds A to the power T. We know already this. This P will transform A to a diagonal form as D using this formula. So P inverse A, P will give you D. This diagonal elements will be exactly equal to this. That's the idea. I repeat, you will get all eigenvectors in a matrix, correct? That is nothing but your P. You find out P inverse. Use this formula. You find out P inverse. P inverse multiplied by A multiplied by P will give you diagonal elements. This diagonal matrix. Those diagonal elements in a diagonal matrix will be exactly equal to the eigenvalues which we have obtained earlier. That's the idea behind. The process of finding P such that P inverse AP equals D is called a diagonalization of the matrix. So this is a definition for your diagonalization of the matrix. A square matrix A is said to be diagonalizable if there exists a matrix P such that D equals P inverse of AP is a diagonal matrix. So D is diagonal matrix. D is a diagonal matrix. So we will solve simple problem. First we will go for 2 by 2 matrix. So A is given as this matrix. To find the eigenvalues, we will have to use A minus lambda I, as I said. A minus lambda I equals 0. So your A is here minus lambda I, which is equal to this, which is equal to 0. Simplify, you will get this equation. Okay, 1 minus lambda multiplied by 4 minus lambda plus 2 equals 0. Simplify, you will get this. You will have a quadratic equation, lambda square minus 5 lambda plus 6. You factorize this equation. So lambda equals 2, 3. 2, 3 are eigenvalues. Is it okay? So first we have found out eigenvalues. The next step will be eigenvectors. eigenvectors. Wait.